black hole a true cosmic prison, where any intruder shall be eternally confined. This invisible boundary is called the event horizon, the most absolute demarcation in the universe, the endpoint of causality, and the limit of known physics. Once this boundary is crossed, all matter shall lose its entire future. All possible world lines converge upon the same endpoint, that place known as the singularity, where spacetime curvature approaches infinity. All known physical laws cease to function. Within this absolute domain ruled by gravity, even the swiftest photons cannot escape its grasp. Trapped like small boats in a waterfall, no matter how they struggle, they can only drift with the current, plunging toward the unfathomable abyss. The event horizon functions like a one-way membrane, permitting matter and information to enter from the outside, yet forever barring any information from escaping within. This absolute irreversibility makes black holes the universe's most perfect prisons. Within this prison, even time loses its former meaning. To outside observers, objects falling into a black hole appear frozen forever on the horizon's surface. Time appears to have ceased flowing. Yet, within the faller's own reference frame, it will reach the singularity within finite time, experiencing what is termed the termination of spacetime. The horror of a black hole lies not only in its capacity for confinement, but in its physical properties that defy conventional imagination. A black hole with 10 times the mass of the Sun possesses an event horizon radius of merely 30 kilometers. This extreme density makes its gravitational field powerful enough to tear apart the fabric of spacetime itself. In this warped spacetime, traditional notions of direction become utterly meaningless. Every path leads to the singularity, just as on Earth's surface, every path leads to the center of the planet. Yet this analogy still falls short, for the geometry within a black hole is far stranger than anything our everyday experience can comprehend. The journey we are about to embark upon will take us deep into every corner of this cosmic prison. We will explore the origins of this prison and witness how stars with masses dozens of times that of the Sun compress themselves into such a space-time singularity. In a spectacular supernova explosion, we will meet the warden of this prison and understand its birth and methods of rule. From stellar mass black holes to the supermassive behemoths at galactic centers, each type of black hole plays a unique role in the cosmos, shaping the destinies of surrounding celestial bodies. We shall also explore the realms governed by this prison, from the 4 million solar mass colossus at our Milky Way's heart, to the cosmic lighthouses blazing within distant quasars. Black holes have left an indelible mark on cosmic evolution. Finally, we shall stand in humanity's shoes, to contemplate the meaning of these cosmic prisons' existence. Before the abyss of infinite space, we reflect on our place in the universe, and the courage that drives our quest for these ultimate mysteries. Now allow me to guide you on this journey through time and space, into this cosmic prison from which even light cannot escape, to unveil its mysterious and terrifying veil. When the core of a massive star transforms into iron, the balance game that has lasted millions of years nears its end. Iron plays a unique role in stellar nuclear fusion, serving as the endpoint for all fusion reactions. The iron nucleus possesses nature's most stable atomic structure. As binding energy reaches its peak, this means that whether splitting or fusing iron nuclei, external energy input is required, rather than releasing energy. This inert iron core acts like an energy black hole within the star. It continuously absorbs energy, yet refuses to release any to resist gravitational compression. At this moment, the star's fate is sealed. The iron core's mass continues to grow. When it reaches the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, electron degeneracy pressure can no longer support such immense mass. Gravity gains absolute dominance. The core region begins a rapid collapse. This process unfolds with astonishing speed. In less than 1/10 of a second, an iron core originally the size of Earth is compressed into a sphere no larger than a city. At such extreme densities, atomic structures are utterly destroyed. Electrons are crushed into atomic nuclei, combining with protons to form neutrons, while releasing vast quantities of neutrinos. This process is known as inverse beta decay. The newly formed neutrons generate immense degenerate pressure, attempting to halt further collapse. When the core density reaches atomic nucleus density, approximately 300 million tons per cubic centimeter, this neutron degenerate pressure suddenly becomes extraordinarily powerful. At this moment, the collapsing core encounters this invisible wall and undergoes violent rebound. Like a compressed spring suddenly released, it generates a powerful shockwave propagating outward. This shockwave advances outward at tens of thousands of kilometers per hour, but it faces immense resistance, needing to break through the outer layers of matter raining down toward the center. At this critical moment, the neutrinos released during the core collapse play the role of savior. Neutrinos are particles that normally interact with matter very little, but at such extreme densities, they have ample opportunity to transfer energy to the shockwave, infusing the shockwave with renewed energy to help it break through the encircling layers. When the shockwave finally penetrates the star's outer layers, one of the universe's most spectacular explosions begins. This is a supernova explosion, whose brightness can briefly outshine an entire galaxy. During the explosion, the star's outer layers are hurled into interstellar space at immense speeds, reaching up to 1/10 the speed of light. This ejected material is rich in elements synthesized throughout the star's lifetime, along with heavier elements formed during the rapid neutron capture process at the moment of explosion. Heavy elements like gold, silver, and uranium in the universe are primarily produced in such supernova explosions. These elements later become the fundamental building blocks of planets and life. Every heavy element atom within our bodies was born in the supernova explosion of some star. After a supernova explosion, depending on the initial mass of the star, different remnants are left behind. When the remaining core's mass ranges from 1.4 to 3.2 times the mass of the Sun, it will form a neutron star. Neutron stars are among the most extraordinary objects in the universe. They compress a mass 1.4 times that of the Sun into a sphere just 20 kilometers in diameter. Their density is unimaginably immense. A teaspoon of neutron star material weighs as much as an entire mountain range on Earth, equivalent to approximately 1 billion tons. This extreme density makes neutron star matter the densest form of matter known, surpassed only by black holes. The gravitational pull at a neutron star's surface is immense, roughly 200 billion times stronger than Earth's gravity. If an object were dropped from a height of 1 meter onto a neutron star's surface, the energy released upon impact would equal the explosion of 100 million tons of TNT. Due to conservation of angular momentum, the collapse of the original stellar core causes neutron stars to spin rapidly. Some neutron stars rotate hundreds of times per second, far faster than any kitchen blender. Simultaneously, neutron stars possess immense magnetic fields, up to 1 quadrillion times stronger than Earth's magnetic field. Such powerful fields can disintegrate atomic structures tens of thousands of kilometers away. When a neutron star's magnetic pole does not align with its rotational axis, the pulsar phenomenon occurs. Radiation beams emitted from the magnetic poles sweep across space like cosmic lighthouses. Whenever this beam points toward Earth, we detect a pulsed signal. The first pulsar was discovered in 1967. Researchers then detected an extremely regular radio pulse signal, with a period of 1.337 seconds, and precision rivaling atomic clocks. They initially suspected it might be a signal from an extraterrestrial civilization, and jokingly dubbed it Little Green Men. We now understand that pulsars are rapidly spinning neutron stars, whose pulse periods correspond to their rotation cycles. These cosmic lighthouses provide astronomers with natural laboratories for studying extreme physics. By observing minute variations in pulsar signal periods, we can detect gravitational waves, investigate the nature of interstellar medium, and even search for exoplanets. Pulsar timing arrays may also help us discover cosmic background gravitational waves. Some neutron stars exist in binary systems, accreting matter from a companion star. This material accumulates on the neutron star's surface and undergoes nuclear fusion, producing periodic X-ray bursts. These X-ray flashes provide invaluable data for studying matter behavior under extreme conditions. When a neutron star accretes mass beyond 3.2 solar masses, even neutron degeneracy pressure cannot withstand gravitational collapse. It will further collapse into a black hole. This is what we will explore in the next section. From the ashes of stellar death emerges the universe's most enigmatic object, that eternal cosmic prison. Now, let us turn our gaze to the construction process of this cosmic prison and trace the origins of its invisible warden. This journey begins with the luminous messengers of the cosmos and the glorious life cycle of stars. Every star is essentially a colossal nuclear fusion furnace. By fusing lighter elements into heavier ones, they release light and heat, illuminating entire planetary systems, sustenance for countless cradles of life across the cosmos. Deep within a star's core, temperature and pressure reach staggering extremes, where millions or tens of millions of kelvins prevail. Atomic nuclei collide violently, overcoming mutual electromagnetic repulsion to achieve nuclear fusion reactions. A star's journey begins with the lightest element, hydrogen. Within the star's core, under extreme heat and pressure, hydrogen nuclei move at immense speeds. When they collide, quantum tunneling allows them to overcome the Coulomb barrier and fuse into heavier helium nuclei. This fusion process incurs a small loss of mass. According to Einstein's famous mass-energy equation, this lost mass converts into immense energy. The energy released from converting just 1 gram of matter is sufficient to power an average household for several years. This energy generated in the core radiates outward in the form of photons and neutrinos. After countless collisions with matter particles, photons slowly traverse the star's layers, potentially taking tens of thousands of years to reach the surface. Ultimately, they radiate into space as sunlight. Within a star, a delicate equilibrium exists between two fundamental forces. One is the inward gravitational force, which attempts to pull stellar matter toward the center. The other is the outward radiation pressure generated by nuclear fusion, which resists gravitational compression. This equilibrium maintains the star's stable form. As hydrogen fuel in the stellar core gradually depletes, the gravitational balance begins to tilt. The core contracts under gravity, causing temperatures and pressures to rise further, creating conditions for the next stage of nuclear fusion. For sun-like stars, the next fusion stage involves helium, where 3 helium nuclei fuse into a carbon nucleus, a process known as the triple alpha process, requiring higher temperatures and pressures. as more positively charged nuclei demand greater energy to overcome mutual repulsion. In more massive stars, nuclear fusion progresses along a complex chain of element synthesis, from hydrogen to helium, from helium to carbon and oxygen, then from carbon and oxygen to heavier elements, such as neon, magnesium, silicon, and others. This chain of element synthesis ultimately halts at iron. The iron nucleus possesses the most stable nuclear structure in nature. As binding energy reaches its peak, this means that whether splitting or fusing iron nuclei, external energy input is required, rather than releasing energy. Within sufficiently massive stars, nuclear fusion processes form onion-like layered structures. The outermost layer consists of unfused hydrogen, followed inward by layers of burning helium, carbon, oxygen, and silicon, culminating in the iron core. The formation of an iron core signals the star's life entering its final countdown, because an iron core cannot generate fusion energy to counteract the gravitational pressure from its outer layers. This inert iron core acts like a ticking time bomb within the star, awaiting the moment to detonate the entire system. In this tug-of-war spanning millions to billions of years, the star's mass plays a decisive role. It acts as a singular key that predetermines the star's life trajectory and ultimate fate. A star's mass dictates its internal temperature and pressure, thereby determining how far its nuclear fusion can progress, and sealing its final destiny at life's end. Stars with masses less than 1/8 of the Sun's cannot achieve the temperatures required for helium fusion in their cores, and will gradually cool to become helium white dwarfs, quietly concluding their existence. Stars with masses between 0.8 and 8 times the Sun's can progress to the carbon-oxygen white dwarf stage. Their endings are relatively tranquil, as they gracefully exit the cosmic stage. By forming planetary nebulae and white dwarfs, stars with masses exceeding 8 times the Sun's face a radically different fate. These cosmic giants, after brief yet brilliant lives, meet the most spectacular deaths, and may give birth to the universe's most enigmatic objects. Nuclear fusion processes within these massive stars proceed at breakneck speed. Like profligate millionaires, they exhaust their nuclear fuel within mere millions of years. This timescale in the cosmic timeline is but the blink of an eye. When these stellar giants finally exhaust their fuel, gravity wins the tug-of-war that has raged for millions of years. The stellar core begins an irreversible inward collapse. This process unleashes unimaginable energy, triggering the most spectacular explosions in the universe. It is within such supernova explosions that new cosmic wonders are born. From the ashes of stellar death, those stellar remnants with sufficient mass will continue their journey of collapse toward infinite density, ultimately forming the cosmic prison mentioned at the outset, that spacetime singularity from which not even light can escape. A star's mass not only determines its own fate, but also whether it can give birth to cosmic extremes like black holes, and dictates the scale and nature of this cosmic prison. From stellar mass black holes weighing a few solar masses, to supermassive black holes spanning millions or even billions of solar masses, their origins are intimately tied to the star's mass. In the following chapters, we will continue to trace the final moments of these massive stars, witnessing how they complete their ultimate transformation into black holes. Amidst the dazzling spectacle of supernova explosions, this will be a cosmic drama of creation and destruction, where mass remains the chief director of the entire play. When the mass of a collapsing stellar core exceeds the critical threshold of 3.2 solar masses, the most intense struggle in the cosmos begins. This is the ultimate contest between neutron degenerate pressure and gravity. 3.2 solar masses. This figure is known as the Oppenheimer-Volkov limit, named after the two physicists who first calculated this critical value in 1939. Above this mass, even one of nature's most powerful repulsive forces, neutron degeneracy pressure, cannot withstand gravity's relentless squeeze. By this stage, the core has endured the baptism of a supernova explosion, having shed most of its outer layers. Yet the remaining core remains too massive. Neutron degeneracy pressure, like a spring compressed to its limit, has reached the peak of its supporting capacity. At such extreme densities, neutrons themselves begin to shatter. They cease to be stable fundamental particles, and instead break down into their more basic quark constituents. This state of matter is called quark matter, whose properties may prove even stranger than neutron matter. Yet even quark degeneracy pressure proves feeble against such immense mass. Gravity, the most fundamental and potent force in the universe, begins to assert its absolute dominance. The core's collapse becomes unstoppable. No known physical force can delay this process. The collapse accelerates rapidly, with both temporal and spatial scales contracting dramatically. Within the framework of general relativity, this collapse is described with greater depth. It is not merely the compression of matter, but the distortion and reshaping of spacetime itself. According to Einstein's field equations, matter and energy dictate how spacetime curves, while the curvature of spacetime dictates how matter moves. During this collapse, the curvature of spacetime grows ever greater, ultimately reaching infinity. All matter converges toward a central point. This point is called a singularity. At the singularity, density, temperature, and spacetime curvature all approach infinity. All known physical laws cease to apply. During the collapse, a critical surface gradually forms. This is the event horizon, when the gravitational pull of collapsing matter becomes sufficiently strong. Its escape velocity exceeds the speed of light. This means nothing can escape from within. The radius of the event horizon is proportional to the mass. For a black hole with 10 times the mass of the Sun, its event horizon radius is approximately 30 kilometers. This surface may not seem particularly large, but remember, contains matter equivalent to 10 times the Sun's mass. From an external observer's perspective, objects falling into the black hole appear frozen forever on the event horizon surface. This is because the extreme gravitational field causes time to dilate dramatically. Time for the object nearly ceases to flow. However, from the faller's own reference frame, they will cross the event horizon within a finite time, and continue plummeting toward the singularity. For a stellar mass black hole, this process may take only a fraction of a second. At the instant of crossing the event horizon, the falling object experiences no distinct tactile sensation. The event horizon is not a solid surface, but a region where the very nature of spacetime undergoes a fundamental transformation. Once inside the event horizon, the roles of time and space undergo a peculiar reversal. The direction of time becomes the direction of space, while the direction of space becomes the direction of time. This means forward motion is no longer a choice, but an inescapable destiny. Within the event horizon, all future-pointing world lines inevitably converge upon the singularity. Just as in the external universe, all futures point toward tomorrow. This is an inevitability deeply embedded in the geometry of spacetime. When matter finally reaches the singularity, it will be compressed to infinite density, and spacetime curvature becomes infinitely large. Our current physics cannot describe what occurs here, requiring quantum gravity theory to unveil its mysteries. At this moment, a stellar mass black hole is formally declared formed. This microscopic cosmic prison completes its construction process. A stellar giant that once illuminated the starry sky has now become a dark cage from which even light cannot escape. This newborn black hole carries most of the original star's angular momentum. If the progenitor star was rotating, a Kerr black hole would form, possessing a more complex structure, including energy shells and an inner event horizon. The uniqueness theorem of black holes tells us black holes have no hair. This means they can only be fully described by three parameters: mass, angular momentum, and charge. All other information is lost during formation. This newborn black hole begins to evaporate, extremely slowly through Hawking radiation. But for stellar mass black holes, this process far exceeds the current age of the universe. They are essentially eternal cosmic structures. Over the next billions of years, this black hole may remain solitary, or form a binary system with another celestial body, or slowly grow by accreting matter, or even merge with another black hole, generating gravitational waves powerful enough to ripple spacetime. The birth of stellar mass black holes marks the conclusion of a star's evolutionary tale, while simultaneously opening a new cosmic chapter. Though these dark celestial bodies no longer emit light, they continue to shape the surrounding universe through gravity. From a radiant star to a light-devouring black hole, this transformation embodies the most extreme physical phenomena in the cosmos and demonstrates the absolute dominance of gravity. Under extreme conditions, the warden of this cosmic prison has taken his post, lurking silently in the universe's darkness, awaiting the next unfortunate celestial body that ventures too close, continuing to enact the cosmic laws governed by gravity. In our next chapter, we will explore the inner workings of this prison, uncover the bizarre properties within the event horizon, and discover how black holes reveal their presence and power through various means. To truly grasp the essence of this cosmic prison, we must transcend Newton's law of universal gravitation and enter the realm of Einstein's general relativity. There, gravity ceases to be a force between two objects, and instead manifests as a geometric effect, the curvature of spacetime itself. Imagine spacetime as a vast elastic membrane. The presence of mass creates a depression in this membrane. This depression is what we perceive as gravity. The greater the mass, the deeper the depression. A black hole is a bottomless hole punched into this membrane. The event horizon marks the boundary of this bottomless hole. Within this boundary, the curvature of spacetime becomes so extreme that all directions point toward the center. Just as on Earth's surface, all directions point downward. In 1916, Carl Schwarzschild discovered the first exact solution for a black hole, while solving Einstein's field equations. This solution describes a static, non-rotating, uncharged black hole, known as a Schwarzschild black hole. The structure of a Schwarzschild black hole is remarkably simple. It is determined by only one parameter, mass. The radius of its event horizon is directly proportional to mass. The formula is twice the gravitational constant multiplied by the mass divided by the square of the speed of light. For a solar mass, this radius is approximately 3 kilometers. At the event horizon of a Schwarzschild black hole, time dilation becomes infinite. This means that to an outside observer, objects falling into the black hole will forever freeze on the horizon. Their clocks appear to have completely stopped ticking. However, the reality is more nuanced. The event horizon is not a solid wall, but a region where space-time properties undergo a fundamental change. Objects passing through it experience no distinct physical sensation. In 1963, Roy Kerr discovered a solution closer to reality. This solution describes a rotating black hole. Most black holes in the universe likely spin rapidly, because they inherit angular momentum from their progenitor stars. The structure of a Kerr black hole is far more complex than that of a Schwarzschild black hole. It is described by two parameters: mass and angular momentum. Rotation causes the black hole to bulge at its equatorial region, much like the rapidly spinning Earth. The most distinctive feature of a Kerr black hole is its ergosphere. The ergosphere is a region just outside the event horizon, where spacetime itself is dragged along by the black hole's rotation, much like a whirlpool in flowing water. Within the ergosphere, objects cannot remain stationary. Even those moving at the speed of light must rotate along with spacetime. This phenomenon is called frame dragging, a key prediction of general relativity. The ergosphere possesses a remarkable property. Objects can enter the ergosphere, gain energy, and then escape. This process is known as the Penrose process, allowing energy extraction from a rotating black hole. A Kerr black hole possesses two event horizons, an outer horizon and an inner horizon. Beyond the inner horizon, the singularity ceases to be a point, and instead forms a ring-like structure. This theoretically enables the possibility of traversing a black hole. However, these theoretical possibilities may not be achievable in real black holes, because the inner horizon may be unstable. Any minute disturbance could lead to catastrophic consequences. Now let's explore extreme physical effects near black holes. First is gravitational time dilation. This effect becomes exceptionally pronounced near black holes. According to general relativity, time passes more slowly in strong gravitational fields. Near the event horizon, the passage of time nearly ceases. This effect has been verified by experiments on Earth. If an astronaut piloted a spacecraft toward a black hole, distant observers would see the spacecraft's speed gradually decrease until it appears frozen on the event horizon, while the astronaut themselves would pass through the horizon normally. Tidal forces represent another crucial effect, arising from the gravitational field's non-uniformity. Much like the moon's gravitational pull on Earth causes ocean tides, when an object approaches a black hole, the gravitational pull on its side closest to the black hole far exceeds that on the side farther away. This gravitational disparity creates a stretching effect. For stellar mass black holes, tidal forces become extremely powerful at great distances. Before a human body crosses the event horizon, it would be stretched into a stream of atoms. This process is known as spaghettification. However, for supermassive black holes, the situation is entirely different. Because their event horizon radii are extremely large, the tidal forces at the horizon are relatively weak. An astronaut might cross the event horizon before experiencing any noticeable effects. Gravitational redshift is another intriguing phenomenon. When light escapes from a strong gravitational field, it loses energy, causing its wavelength to lengthen, and its color to shift toward the red end of the spectrum. Near a black hole, this effect becomes extremely pronounced. At the event horizon, gravitational redshift becomes infinite, meaning any photon would lose all its energy, which is precisely why light cannot escape from a black hole. These extreme physical effects exist not only in theory, but have been observed in the cosmos. Through precise observations of binary star systems, we have verified the prediction of gravitational time dilation. Observations from the Laser Interferometer Gravitational Wave Observatory have also confirmed that the ripples in spacetime produced during black hole mergers are in perfect agreement with the predictions of general relativity. The image of a black hole captured by the Event Horizon Telescope directly reveals the characteristics of the black hole's shadow. The size and shape of this shadow are in perfect alignment with the predictions of general relativity. Understanding the geometric structure and properties of black holes not only allows us to comprehend the architecture of this cosmic prison, but also deepens our grasp of the nature of spacetime. These insights are propelling the advancement of physics and guiding us toward new frontiers in quantum gravity theory. In the following sections, we will observe how these geometric properties manifest through specific astronomical phenomena, from the generation of luminous jets in accretion disks to the emission of gravitational waves. In its own unique way, the black hole proclaims its presence to the cosmos. When a star wanders through the cosmos, if it ventures too close to a black hole, it begins one of the universe's most spectacular death dances. The first step of this dance is the star's capture. The black hole's gravitational field begins to exert its influence. As the star approaches, it first experiences tidal forces. These forces arise from gradients in the gravitational field, much like the moon's gravitational pull causing tides on Earth. But a black hole's tidal forces are countless orders of magnitude stronger. When the star crosses the Roche limit, the gravitational pull exerted by the black hole on the star's near side significantly exceeds that on the far side. This disparity surpasses the star's own gravitational binding energy. The star begins to stretch and deform. Initially, the star only undergoes slight deformation, transforming from spherical to ellipsoidal. As the star continues its approach, this deformation becomes increasingly pronounced, gradually stretching the star into a thin stream. This process is termed spaghettification. At the instant the star is completely torn apart, enormous energy accumulates within it. Half of the stellar material is hurled into distant interstellar space, forming brilliant nebulae. The other half falls toward the black hole along complex orbits. This captured matter does not plunge directly into the black hole. Due to conservation of angular momentum, it forms a rotating disk around the black hole. This is the precursor to an accretion disk. The accretion disk is the primary stage where black holes display their power. Within this disk, matter rotates at speeds approaching the speed of light. Matter at different radii possesses different angular velocities, leading to intense shear forces. Friction between particles generates immense heat. This friction is not merely mechanical. More significantly, it involves magneto-hydrodynamic processes. Magnetic field lines within the disk become twisted and entangled, producing magnetic turbulence and magnetic reconnection. These processes efficiently convert kinetic energy into thermal energy. The temperature distribution in an accretion disk exhibits a gradient. Near the innermost region, close to the event horizon, temperatures can reach millions to billions of Kelvin. At such extreme heat, matter is not only ionized into plasma, but even atomic nuclei undergo partial dissociation. The superheated accretion disk emits intense electromagnetic radiation, spanning the entire electromagnetic spectrum, from radio waves to gamma rays. The most prominent emission is X-ray radiation, which can be detected by space telescopes, serving as crucial clues for discovering black holes. During accretion, magnetic fields play another crucial role, extracting rotational energy from the black hole to form relativistic jets aligned with its spin axis. These jets erupt at near-light speeds, extending millions of light-years. Particles within the jets are accelerated to immense energies, emitting radiation across the entire spectrum from radio to gamma rays. The formation mechanism of jets is highly complex. It may involve the energy layer effect of black holes and magnetic processes within the accretion disk. When magnetic field lines are twisted by the black hole's rotation, they store energy like a coiled spring, and are eventually released in the form of directed jets. Throughout this process, the black hole reveals its essence as the universe's most efficient energy converter. Its energy conversion efficiency is astonishing. Nuclear fusion powers stars, converting approximately 0.7% of rest mass into energy, while black hole accretion processes can convert up to 40% of rest mass into energy, an efficiency over 60 times greater than nuclear fusion. This extraordinary efficiency stems from the black hole's extreme gravitational field. As matter falls toward the black hole, its gravitational potential energy is converted into light and heat. This process is far more efficient than any human-made generator. In active galactic nuclei, a black hole's energy output can surpass that of its entire host galaxy. A black hole with a mass merely millions of times that of the Sun may shine 1,000 times brighter than a galaxy containing hundreds of billions of stars. This energy is released not only through radiation, but also via jets and outflows that profoundly influence the evolution of their host galaxies. They may regulate star formation rates and even determine the ultimate fate of entire galaxies. The tidal disruption event observed by astronomers in 2018 provided a perfect laboratory for studying this process. During the event, they detected full-spectrum radiation from radio to X-rays and witnessed the formation of relativistic jets. Through these observations, we can measure black hole mass and spin, study the physics of accretion disks, and even test general relativity's predictions in strong gravitational fields. Each tidal disruption event is a moment when black holes bare their fangs to the universe, and a precious opportunity for us to understand these mysterious objects. In this dance of destruction, we witness gravity's absolute dominion and the ultimate fate of matter under extreme conditions. When this dance concludes, the star's material is either hurled into interstellar space to become raw material for the next generation of stars and planets, or sinks forever beyond the black hole's event horizon, becoming a new prisoner in this cosmic prison. In our ongoing exploration, we shall continue to lift the veils shrouding black holes and witness how humanity harnesses its ingenuity to capture the faintest traces of these dark behemoths' existence. Though black holes themselves emit no light, humanity, through wisdom and technology, has developed multiple methods to indirectly prove their existence. The first crucial method involves X-ray binary systems. In close binary star systems, when one star evolves into a black hole, it draws matter from its companion star. As this matter falls toward the black hole, it forms a high-temperature accretion disk, emitting intense X-ray radiation. Cygnus X1 is humanity's first discovered stellar mass black hole candidate. In this system, a blue supergiant star approximately 20 times the mass of the Sun orbits an invisible object, whose mass is about 15 times that of the Sun, far exceeding the upper mass limit for neutron stars. By analyzing the time-varying characteristics of X-ray radiation, we can infer the physical conditions within the inner region of the accretion disk. Certain X-ray binaries exhibit quasi-periodic oscillations, which may be related to black hole rotation or instabilities in the accretion disk, providing a unique window for studying physics in strong gravitational fields. The second key method is stellar kinematics measurements. This technique is particularly effective for detecting supermassive black holes at galactic centers. At the heart of our Milky Way galaxy, astronomers have continuously monitored the orbital motions of multiple stars for decades. These stars orbit an invisible gravitational source at high speeds. One such star, designated S2, travels at nearly 20 million kilometers per hour along a highly elliptical orbit, By precisely measuring the orbital parameters of these stars, we can calculate the mass of the central object using Kepler's laws. Calculations reveal a colossal entity 4 million times the mass of the Sun, confined within an area smaller than Neptune's orbit. Such immense mass concentrated in such a small space strongly suggests the presence of a supermassive black hole. The third method involves gravitational lensing. According to general relativity, massive celestial bodies warp the surrounding spacetime, causing passing light rays to bend, much like an optical lens. When a black hole happens to align between a background star and our line of sight, it creates a microgravitational lensing event. The brightness of the background star temporarily increases. By analyzing this light curve, we can infer the mass of the intermediate object. While this method cannot directly distinguish black holes from other compact objects, it offers the possibility of discovering isolated black holes. Yet these indirect methods failed to satisfy humanity's desire to see a black hole directly, until the birth of the Event Horizon Telescope. This ambitious project linked radio telescopes worldwide to form a virtual telescope with an effective aperture equivalent to Earth's diameter. In 2017, the Event Horizon Telescope observed two significant targets: Sagittarius A** at the center of the Milky Way, and the supermassive black hole at the heart of the elliptical galaxy M87. To understand how the EHT photographed a black hole, we must recognize that the black hole itself is invisible. What we actually observe is the shadow of the black hole, the dark outline of its event horizon projected against the luminous background of its accretion disk. Due to the black hole's intense gravitational field, light from the accretion disk is severely bent, causing significant distortion in the observed image. We can also see the portion behind the black hole, forming a bright ring. On April 10, 2019, the EHT collaboration released humanity's first-ever image of a black hole. This image depicts the black hole at the center of the M87 galaxy, with a mass 6.5 billion times that of the Sun. The bright ring in the photograph perfectly matches the predictions of general relativity. The diameter of the black hole's shadow is approximately 40 billion kilometers, equivalent to 3 times the diameter of Neptune's orbit. This size aligns with theoretical calculations based on the black hole's mass. On May 12, 2022, the EHT released an image of the black hole at the center of the Milky Way. Although this black hole has only 1,000th the mass of the M87 black hole, its apparent angular size in the sky is comparable, due to its proximity being 2,000 times greater. Beyond observing black holes through electromagnetic waves, we can also detect their mergers via gravitational waves. Gravitational waves are ripples in spacetime itself, generated by the accelerated motion of massive celestial bodies. When two black holes orbit each other, they lose energy by emitting gravitational waves, causing their orbital decay, until they eventually merge, forming a larger black hole. This process releases immense gravitational wave energy. September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, first directly detected gravitational waves. The signal originated from the merger of two black holes with masses of 36 and 29 solar masses, respectively. This discovery ushered in a new era of gravitational wave astronomy. In the final moments before merger, the two black holes orbit each other at speeds exceeding half the speed of light, emitting gravitational wave signals with rapidly increasing frequency and amplitude. This segment of the signal is known as the chirp. By analyzing this signal, we can precisely determine the black hole's mass and spin. The intensity of gravitational waves produced at the moment of merger reaches its peak. Subsequently, the newly formed black hole gradually relaxes to a stable state by emitting quasi-normal mode gravitational waves. Much like the lingering resonance of a struck bell, gravitational wave detection provides a novel window into studying black holes. By analyzing gravitational wave signals, we can measure black hole mass and spin, test predictions of general relativity in strong field regions, and even explore how black hole merger rates evolve over cosmic time. In the future, with the addition of more gravitational wave detectors, including space-based detectors like LISA, we will be able to detect mergers of even more massive black holes, further expanding our understanding of black hole populations. From X-ray observations to stellar dynamics, from the Event Horizon Telescope to gravitational wave detection, each method offers a unique perspective on understanding black holes. These observational approaches complement and validate one another. Together, they build a robust chain of evidence for black hole existence. In the following chapters, we will depart from these relatively small stellar mass black holes and venture into the vast realms at the centers of galaxies to explore those supermassive behemoths whose masses reach millions or even billions of times that of the Sun. At the heart of our Milky Way galaxy lies a cosmic-scale supermassive monster known as Sagittarius A star. Though this enigmatic celestial object has never been directly observed, its immense gravitational pull subtly governs the entire structure and motion of the Milky Way. As early as the 1960s, astronomers used radio telescopes to discover a powerful radio source at the galactic center. This source was designated Sagittarius A star. Its position aligns almost precisely with the geometric center of the Milky Way. Initial observations revealed this radio source to be extremely compact, with an angular diameter of a mere 30 millionths of a degree, equivalent to viewing a tennis ball on the moon from Earth. Such a minuscule size suggested immense mass within. Advancements in observational technology, particularly in infrared wavelengths, astronomers gained the ability to penetrate the dust of the galactic disk and directly observe stellar motion at the galactic center. In the 1990s, two independent research teams, led by Genzel and Giz respectively, initiated long-term monitoring programs of stars near the galactic center. Using telescopes at the European Southern Observatory and the Keck Observatory, they continuously tracked the orbital motions of dozens of stars. These observations revealed a startling fact. Stars near the galactic center move at astonishing speeds. Some stars orbit at velocities exceeding 5,000 kilometers per second, equivalent to 2% of the speed of light. Such high velocities within such a small region necessarily indicate the presence of an extremely massive source. The most famous of these stars is S2. Its orbital period is a mere 16 years. At its closest approach, it passes within just 170 astronomical units of the central radio source, nearly 4 times closer than Pluto orbits the Sun. At this closest point, its speed reaches a staggering 7,650 kilometers per second. By precisely measuring these stars' orbits, astronomers can apply Kepler's third law to accurately calculate the central object's mass. The results reveal a colossal entity 4 million times the mass of the Sun, confined within a region smaller than Mercury's orbit. Such immense mass concentrated in such a tiny space rules out any known cluster of compact celestial bodies. The only plausible explanation is a supermassive black hole, beyond stellar dynamics evidence. Sagittarius A* exhibits other hallmarks of a black hole. It undergoes rapid fluctuations in radiation flux, on timescales ranging from hours to days. These rapid variations indicate the source region must be extremely compact. Otherwise, changes in different parts would cancel each other out. By analyzing the temporal structure of these flares, astronomers deduced Sagittarius A**'s event horizon radius is approximately 6 million kilometers, equivalent to 1/10 of Mercury's orbital radius. This value perfectly matches the theoretical prediction based on its mass. Despite its immense mass, Sagittarius A** exhibits relatively low luminosity and currently resides in a dormant state. This low luminosity phase may correlate with a low accretion rate. With only about 10 solar masses of material accreted per second. Yet even in dormancy, Sagittarius A** still dominates the entire galactic architecture through gravity. Its gravitational influence governs stellar motion across thousands of light years, shaping the overall structure of the galactic center region. Within a few light years of the black hole, stellar density reaches millions of stars per cubic light year, 1,000,000 times higher than the density near the Sun. This extreme stellar density is a direct consequence of the central black hole's gravitational influence. The spiral arm structure of the Milky Way may also be linked to the presence of Sagittarius A*. Although a direct causal relationship remains unconfirmed, theoretical models suggest the central black hole can influence the stability of the galactic disk through dynamical friction. On a larger scale, Sagittarius A** shapes the gravitational potential well of the entire galaxy. Together with other matter, it determines the shape of the Milky Way's rotation curve and the distribution of dark matter within the galactic halo. The distribution of globular clusters at the Milky Way's center also exhibits a connection to Sagittarius A*. These ancient clusters appear to orbit the central black hole, forming a vast system, much like planets revolving around the Sun. Even more astonishingly, Sagittarius A** may have played a pivotal role in the formation and evolution of the Milky Way. In the early universe, it may have been an active quasar, regulating star formation rates through jets and radiation. Now Sagittarius A** is relatively quiet, but astronomers have detected a significant outburst occurring approximately 350 years ago. This outburst left behind reflected light signals in nearby molecular clouds. Analysis of these reflected signals. We learned that in the late 17th century, Sagittarius A** shone 1,000,000 times brighter than today. This outburst may have been linked to a major accretion event. In the future, when molecular clouds or other celestial bodies approach Sagittarius A**, similar outbursts could occur again. At that time, we may have the opportunity to witness firsthand the spectacular sight of this cosmic beast awakening. Research into the Milky Way's center continues. New telescopes and technologies continually yield fresh discoveries. For instance, the discovery of G-objects. These peculiar objects resemble dust clouds, yet exhibit stellar-like dynamical properties. They may be massive stars stripped of their outer atmospheres. These findings not only enrich our understanding of the galactic center, but also provide crucial insights for comprehending supermassive black holes at the cores of other galaxies. As the closest supermassive black hole to us, Sagittarius A** serves as the premier laboratory for studying these cosmic behemoths. Through continuous observation of its properties, we are gradually unraveling the mysteries of the coevolution between galaxies and their central black holes. Now allow me to guide you temporarily away from the Milky Way's center and turn our gaze toward the deeper, more distant reaches of the universe. There exist even larger and more active cosmic behemoths. They demonstrate the absolute dominance of black holes. In a more direct manner, when a supermassive black hole at the heart of a galaxy awakens from dormancy, and begins violently devouring surrounding matter. It ignites the brightest beacons in the cosmos. These are quasars. The English term quasar means quasi-stellar object. The discovery of quasars began in the 1960s. During sky surveys, astronomers observed celestial bodies resembling ordinary stars, yet their spectra revealed massive redshifts, indicating they were receding from us at extreme speeds, and were actually located in the distant depths of the cosmos. Further observations revealed a startling truth. These seemingly faint stellar points actually possessed a combined luminosity equivalent to thousands of ordinary galaxies. Yet their diameters were astonishingly small, less than 1 light-year. This is several orders of magnitude smaller than the Milky Way's diameter of 100,000 light-years. Such immense energy emanating from such a minuscule region leaves only one plausible explanation: a supermassive black hole with a mass millions to billions of times that of the Sun is devouring matter at a rate approaching the Eddington limit. During this violent accretion process, before matter plunges into the event horizon, it converts gravitational potential energy into radiated energy. This energy conversion efficiency can reach 40%, far surpassing the 0.7% efficiency of stellar nuclear fusion. The core structure of a quasar exhibits typical hierarchical features. At its very center lies the supermassive black hole itself. Surrounding it is an optically thick accretion disk. Temperatures range from several thousand Kelvin at the outer edge to hundreds of thousands of Kelvin at the inner edge. The radiation emitted by the accretion disk peaks in the ultraviolet spectrum. This intense ultraviolet radiation further ionizes the outer gas clouds, forming the so-called broadline region and narrowline region. The broadline region lies near the black hole. Gas clouds move at thousands of kilometers per second. Their emission lines are significantly broadened by the Doppler effect. The narrowline region is farther away. Gas clouds move more slowly. Emission lines are relatively narrow. In some quasars, relativistic jets can also be observed. These jets extend perpendicular to the accretion disk plane, at speeds approaching the speed of light. When the jet direction aligns with Earth's line of sight, we observe exceptionally bright blazars. Quasars exhibit an extremely broad spectral energy distribution, spanning from radio wavelengths to gamma rays. This all-wavelength radiation characteristic enables comprehensive study of their physical processes through multi-wavelength combined observations. As observational data accumulates, astronomers have discovered that quasars are merely one member of the active galactic nucleus, AGN, family. This family also includes Seyfert galaxies, BL Scorpius objects, radio galaxies, and other types. To explain these seemingly diverse phenomena, astronomers proposed the unified model of active galactic nuclei. This model posits that all these objects are fundamentally identical, with observed differences primarily stemming from viewing angles. Within the unified model, a structure known as the dusty torus surrounds the black hole. This torus blocks some radiation. When viewed edge-on, only the narrowline region is visible, corresponding to Seyfert 2 galaxies. When viewed along the polar axis, the line of sight aligns directly with the broadline region and central engine. This corresponds to Seyfert I galaxies, or quasars. When the jet is precisely aligned with our line of sight, the Doppler effect significantly amplifies brightness, resulting in blazars, where radiation predominantly originates from the jet rather than the accretion disk. The unified model also accounts for intrinsic factors, such as black hole mass and accretion rate, which determine the absolute luminosity and mass output of active galactic nuclei. observational evidence continues to support the unified model. For instance, in some Seyfert 2 galaxies, polarization observations have indeed detected the obscured broad lines, while infrared observations directly reveal thermal radiation from dusty annuli. Quasars and active galactic nuclei hold significant cosmological importance. They are not only the most distant celestial objects, but also crucial tracers of early cosmic evolution. By studying high-redshift quasars, we can explore the distribution of matter and the formation of structures in the early universe. The most distant quasars exhibit redshifts exceeding 7. This implies we are observing scenes from when the universe was less than 1 billion years old. The existence of these primordial quasars poses a formidable challenge to theories of supermassive black hole formation. The intense radiation and jets from quasars exert profound effects on their host galaxies. They may regulate star formation within galaxies through feedback mechanisms, and even determine a galaxy's ultimate fate. When a quasar depletes its surrounding fuel, it gradually dims, returning to quiescence, much like Sagittarius A** in our Milky Way, entering a dormant state, awaiting the next accretion event. Modern sky surveys like the Sloan Digital Sky Survey have discovered hundreds of thousands of quasars. These large sample statistical studies reveal the overall characteristics and evolutionary patterns of the quasar population. By studying the spatial distribution of quasars, we can also explore the large-scale structure of the universe. As bright background sources, quasars can reveal the distribution of absorbing matter between them. Quasar research has spanned over half a century, yet they retain an air of mystery. Each advancement in observational technology brings new discoveries and insights. Future telescopes like the 30-meter telescope and the James Webb Space Telescope will enable us to observe even more distant quasars and explore the earliest stages of black hole formation in the universe. In studying these cosmic engines, we witness not only the ultimate expression of gravity, but also the magnificent chapter of cosmic matter cycling and energy transformation. Each quasar narrates the cosmic tale of coevolution between galaxies and their central black holes. When the universe was less than 1 billion years old, supermassive black holes, massive enough to devour billions of suns, already existed. This discovery plunged astronomers into profound perplexity. How did these cosmic behemoths grow to such staggering sizes in such a fleeting span of time? According to standard accretion theory, even at the Eddington limit rate of continuous accretion, a seed black hole of solar mass would require billions of years to evolve into a supermassive black hole, far exceeding the age of the universe itself. This temporal contradiction has given rise to a core enigma in modern astrophysics. Where did the seeds of supermassive black holes originate? And through what mechanisms did they achieve such rapid early growth? Current mainstream hypotheses fall into several camps. The most widely discussed is the direct collapse model. This model posits that, in the unique conditions of the early universe, massive primordial gas clouds could collapse directly into supermassive black holes. Before the cosmic reionization epoch, the first generation of gas clouds, devoid of heavy elements, lacked effective cooling mechanisms to fragment into ordinary stars. Instead, they collapsed directly into colossal celestial bodies. The mass of these gas clouds could reach hundreds of thousands to millions of times that of the Sun. Their collapse process differed from star formation by skipping a series of intermediate steps and directly forming seeds for supermassive black holes. The mass of these seed black holes reached thousands to tens of thousands of solar masses from the outset. laying a solid foundation for subsequent rapid growth. Another significant hypothesis is the merger growth model. This model posits that the initial seeds were smaller stellar mass black holes. Through repeated mergers and accretion, they gradually grew larger, like a snowball gathering momentum. In the high-density environments of the early universe, encounters between black holes were more frequent. Driven by gravitational friction, they gradually settled toward the centers of dark matter halos. There, frequent merger events occurred. Each merger not only increased the black hole's mass, but also provided fresh accretion fuel. This stepwise growth mechanism may have significantly accelerated black hole evolution. An intriguing alternative perspective suggests the existence of hypermassive stars in the early universe. These stars could have reached hundreds of solar masses, with extremely short lifespans, collapsing directly into massive black hole seeds upon death. The formation of these hypermassive stars benefited from unique conditions in the early universe, such as higher background temperatures and a pure composition lacking heavy metals, which favored the formation of more massive stars. Observational evidence is gradually accumulating. Deep field observations from the James Webb Space Telescope have uncovered an increasing number of high redshift quasars, whose properties provide crucial constraints for early black hole formation models. These observations reveal that at redshifts above 7, when the universe was less than 800 million years old, black holes with masses of 1 billion solar masses already existed. This poses a severe challenge to all formation theories. Theoretical physicists are exploring more extreme possibilities, including the primordial black hole hypothesis. This hypothesis suggests that extreme density fluctuations in the early universe could directly collapse into black holes of varying masses. Another possibility is rapid growth of early black holes through super-Eddington accretion. In this model, the accretion rate can far exceed standard limits. Although radiation efficiency decreases, mass growth becomes significantly faster. Current research indicates the actual history of black hole growth may result from the combined effects of multiple mechanisms, different seed formation mechanisms, and different growth pathways may dominate independently in different cosmic eras and environments. Future observations will help distinguish these models. In particular, laser interferometer space antenna will detect black hole mergers in the early universe, providing direct evidence for seed black hole formation mechanisms. Observations from 30-meter class ground-based telescopes will enable us to observe even earlier black hole populations. Statistical studies will reveal the evolutionary history of the black hole mass function. The origin of supermassive black holes is not only crucial for understanding black holes themselves, but also intimately linked to the formation and evolution of galaxies. The coevolution of black holes and their host galaxies represents a frontier topic in modern astrophysics. The answer to this unsolved mystery may lie hidden in the physics of the early universe, which we have yet to fully comprehend. Could involve deeper questions, such as the nature of dark matter. Each observation of distant quasars offers a glimpse into the cosmos' infancy. Each theoretical model constructed expands the frontiers of human knowledge. In this quest, we pursue not only the origins of black holes, but also the very structure and evolutionary patterns of the universe itself. The ultimate resolution of this question may fundamentally reshape our understanding of the cosmos. With the deployment of next-generation observational instruments and the continuous advancement of theoretical research, we now stand at the threshold of unraveling this century-old enigma, the mystery of supermassive black hole origins. will soon be unveiled in the near future. Within the framework of classical general relativity, black holes were perfect prisons, impenetrable, inescapable, devouring everything without ever releasing anything. This image was overturned in 1974 by a young physicist, Stephen Hawking. Hawking introduced quantum mechanics into black hole research and discovered a startling phenomenon. Black holes are not entirely dark. They emit faint radiation. This discovery fundamentally transformed our understanding of black holes. To comprehend Hawking radiation, we must rethink the vacuum from the perspective of quantum field theory. In quantum mechanics, the vacuum is not empty. It is filled with quantum fluctuations. Virtual particle pairs constantly emerge and annihilate within an infinitesimal time span. These pairs consist of a positive energy particle and a negative energy particle. They borrow energy to exist briefly before annihilating each other within a permissible time frame to return the borrowed energy. In flat spacetime, this process yields no net effect on average. However, near a black hole's event horizon, the intense gravitational field alters this picture. When virtual particle pairs are created near the event horizon, a special case may occur, where the negative energy particle crosses the event horizon and falls into the black hole, while the positive energy particle escapes to distant regions. To an external observer, the black hole appears to emit a real particle. This process effectively extracts energy from the black hole, because the fallen negative energy particle actually reduces the black hole's mass. Through intricate calculations, Hawking demonstrated that this radiation exhibits a perfect thermal spectrum. A black hole behaves like a thermodynamic blackbody, whose temperature is proportional to its surface gravity and inversely proportional to its mass. For a black hole with solar mass, this Hawking temperature is merely 10 Kelvin, far below the temperature of the cosmic microwave background radiation. This implies that in the current universe, the mass lost by black holes through Hawking radiation is vastly smaller than the energy they absorb from the background radiation. However, as the universe expands, the background radiation temperature will continue to drop. In the distant future, when the cosmic temperature falls below the Hawking temperature of black holes will begin to lose mass net. The discovery of Hawking radiation led to deeper questions, namely the famous black hole information paradox. In purely classical theory, information carried by matter falling into a black hole appears to be lost forever. This contradicts fundamental principles of quantum mechanics. Quantum mechanics demands the conservation of information. The evolution of a system should be a unitary process. Information cannot truly vanish. Yet, after a black hole evaporates, the information of the original matter that fell into it appears to disappear along with it. This paradox sparked decades of debate. Hawking himself initially believed information was indeed lost, which created a severe conflict with quantum mechanics. Many other physicists, especially string theorists, firmly maintained that information must be preserved in some manner. Potential solutions include information being encoded and carried out via Hawking radiation, or stored within the remnants left after evaporation, or even preserved through some holographic principle on the two-dimensional surface of the event horizon. Recent research indicates information is likely indeed preserved by calculating the entanglement properties of particles in Hawking radiation. Physics has discovered that information may leak out from black holes through subtle mechanisms. Research into the black hole information paradox has driven the exploration of quantum gravity theory. It compels physicists to contemplate the profound connection between spacetime and quantum information. If Hawking radiation truly exists, it will determine the ultimate fate of black holes. As a black hole's mass diminishes, its temperature will steadily rise, its radiation rate will accelerate. At the final moment, the black hole may undergo a violent explosion, releasing vast quantities of high-energy particles. The details of this process remain an active field of research. For stellar mass black holes, the timescale of evaporation far exceeds the current age of the universe. But for primordial black holes that may exist, they could be exploding in today's universe. The theory of Hawking radiation intricately links general relativity, quantum mechanics, and thermodynamics. In a remarkable way, it suggests that black holes may possess deeper structures, far beyond our current understanding. This discovery not only transformed our understanding of black holes, but also profoundly influenced the development of fundamental physics. It provides crucial clues for comprehending the nature of spacetime and advancing quantum gravity theory. On the journey to unravel the mysteries of black holes, Hawking radiation is merely a starting point. It opens a door to deeper understanding. The view beyond may be more wondrous than we imagine. When we contemplate how these microscopic quantum processes operate within the largest celestial bodies in the universe, we marvel at the exquisite unity of natural laws. From the tiniest quantum fluctuations to the grandest black hole evolution, all obey the same physical principles. This unity may well be the universe's deepest secret, and the very source of humanity's confidence in rationally exploring cosmic mysteries. Black holes are not solitary entities in the cosmos, but share profound and intricate connections with their host galaxies. This coevolutionary relationship weaves the fabric of galactic formation and evolution, like warp and weft on a cosmic loom. Observational data reveal a striking pattern. The mass of a galaxy's bulge shows a significant positive correlation with the mass of its central black hole. This discovery suggests that the growth of black holes and the evolution of galaxies share a common history. A more precise relationship emerges from the M-sigma relation, the mass of a black hole and the velocity dispersion of stars in the galactic bulge. This empirical relationship indicates an intrinsic physical connection between black hole growth and galactic dynamical evolution. In the early cosmic era, black holes and galaxies may have commenced their formation journeys simultaneously. Dark matter halos within primordial density fluctuations provided gravitational potential wells for gas accumulation. This gas could form stars or fall toward the center to nourish black holes. Through accretion, black holes release immense energy. Intense radiation and relativistic jets exert significant influence on their host galaxies. This feedback mechanism may regulate stellar formation and even determine a galaxy's ultimate fate. During periods of intense black hole activity, strong radiation pressure and jet shocks can disperse cold gas within the galaxy. This cold gas serves as the raw material for star formation. Its depletion suppresses new star formation. In certain scenarios, black hole feedback may trigger starburst activity by compressing molecular clouds and promoting star formation. Evidence for this positive feedback has been increasingly observed in recent years. Black hole mergers play a crucial role in galactic evolution. When two galaxies merge, their central black holes gradually approach, eventually coalescing into a larger black hole. This merger process releases immense gravitational waves and may alter the black hole's spin direction. Galaxy mergers also supply fresh fuel to black holes, triggering renewed accretion activity. In the formation of the large-scale structure of the universe, black holes similarly play a vital role. as powerful gravitational sources. They influence the distribution of matter throughout the cosmos. The brightest galaxies within clusters typically host the largest supermassive black holes. These black holes may sink to the center of dark matter halos through dynamical friction, influencing the entire cluster's dynamical evolution. The intense radiation from early universe quasars may have significantly contributed to cosmic reionization. These high-energy photons could ionize neutral hydrogen, altering the universe's transparency and thermal history. Black holes may also influence the chaining process of cosmic structure formation. At the nodes of the cosmic web, the presence of supermassive black holes may alter the cooling and aggregation mechanisms of gas. The latest cosmological simulations reveal that without accounting for black hole feedback effects, simulation results exhibit systematic discrepancies with observational data. This further confirms the pivotal role of black holes in cosmic evolution. The emergence of gravitational wave astronomy has opened a new window for studying black hole populations. By analyzing the statistical properties of black hole mergers, we can trace the growth and evolution of black holes. Throughout cosmic history, future observations will enable us to construct a more complete picture of black hole evolution, from the first black holes at the dawn of the universe to the cosmic behemoths of today. Their lifetimes will be intricately linked to the evolution of galaxies. In this grand cosmic panorama, black holes are no longer solitary cosmic prisons, but vital nodes in the web of cosmic evolution. They embody the ultimate expression of gravity and serve as pivotal links connecting structures across cosmic scales. Understanding black holes' role in cosmology touches not only core questions of astrophysics, but also the very nature and evolutionary laws of the universe. Each exploration of black holes represents a step toward deeper cosmic understanding. As we gaze upon the universe's profound night sky, those invisible black holes are shaping everything we see in their own unique way, from the birth, life, death, and decline of stars to the evolution and transformation of galaxies. Everywhere bears the imprint of black holes. Upon this cosmic loom, black holes stand as enigmatic weavers, alongside dark matter and dark energy, weaving the past, present, and future of the universe. Their secrets await our continued exploration and discovery. From the birthlight of a star to the eternal dark prison of a black hole, we witness a cosmic epic spanning billions of years, a magnificent narrative of matter and energy, time and space. In the brilliant life of stars, we see the universe's most generous side, forging fundamental elements into the building blocks of life. In the profound event horizons of black holes, we see the universe's harshest side, reducing all to infinite silence. This path from light to darkness reveals the fundamental laws governing the cosmos, the exquisite balance between gravity and nuclear forces, forged the long, stable era of stars, yet gravity's ultimate triumph forged the absolute reign of black holes. On the cosmic scale, humanity is but an insignificant speck. Our planet is merely a speck of dust in the boundless void. The history of our civilization is but a blink compared to the age of the universe. Yet it is this insignificant existence that strives to comprehend it all. With our intellect, we construct theories to explain the cosmos. With our technology, we capture the shadow of a black hole. From Newton's universal gravitation, to Einstein's warped spacetime, to Hawking's quantum evaporation, human understanding continually pushes beyond the boundaries of imagination. Each theoretical leap is a bold exploration of the unknown frontiers by reason. When we gaze upon a black hole, we are truly contemplating the frontier of human knowledge. Beyond that event horizon lies the physics we have yet to comprehend. It may be the domain of quantum gravity, the testing ground for string theory, or the birthplace of entirely new physics. With its extreme existence, the black hole continually challenges the limits of our understanding. The information paradox forces us to rethink the relationship between quantum mechanics and general relativity. Hawking radiation offers glimpses of the profound connection between thermodynamics and gravity. In this journey of exploration, we uncover not only cosmic mysteries, but also the power of human reason. Though as insignificant as dust, we dare to question ultimate truths, striving to comprehend the universe's origin and end. From Galileo's first gaze through a telescope at the stars, to the Event Horizon Telescope capturing black hole images, this journey of exploration has borne witness to human courage and wisdom. Each breakthrough in observational technology has deepened our understanding of the cosmos. Now we stand at a new starting point. Gravitational wave astronomy allows us to listen to the ripples of spacetime. Next-generation telescopes will take us back to the dawn of the universe. Quantum computers may help us simulate the interior of black holes. Every technological advancement is a new gaze we cast into the depths of the cosmos. In this vast cosmos, humanity may be fleeting and insignificant, but our courage in pursuing truth, our resolve to explore the unknown, establishes a unique connection between us and this magnificent universe. As we conclude this cosmic journey, let us carry reverence for nature's laws and curiosity about knowledge's frontiers, to continue seeking our place and purpose amidst this boundless sea of stars. Now please close your eyes. Let your thoughts gently return. Store the vastness of the cosmos within your heart. Breathe in the serenity of the starry sky. In this infinite universe, your very existence is a miracle. Let this tranquility accompany you to sleep. Continue your journey through the cosmic seas in your dreams. Now, gently withdraw your thoughts from that all-consuming event horizon. Let your gaze drift away from the violent accretion disk and relativistic jets. As this journey through time and space draws to a close, let us together experience the universe's most fundamental gift, eternal silence. The fury of black holes will eventually settle into stillness. The splendor of stars will fade into darkness. In this boundless void, echoes a stillness deeper than any sound, a cosmic essence, transcending time and life itself. Recall the journey we've traversed, from stellar fusion furnaces to supernovas' magnificent explosions, from neutron stars' bizarre structures to black holes' event horizons. Each exploration reveals that before the grand narrative of the cosmos, all clamor is but a fleeting echo. Now, let this reverence for the vast sea of stars slowly settle into inner peace. Let the eternal silence of the universe soothe the disturbances of daily life. In the depths of this boundless darkness lies the most profound tranquility. Breathe deeply. Feel your connection to this vast sea of stars. Each breath you take contains dust from ancient stars. Each beat of your heart echoes the rhythm of cosmic evolution. In this infinite spacetime, your very existence is the most beautiful miracle. Now, let your eyelids gently close. Let your body gradually relax. Entrust your consciousness to this sea of stars. Let the spiral arms of the Milky Way gently enfold you. Let the stillness of darkness gently embrace you. May the eternal tranquility of the cosmos accompany you into deep slumber. May the tender whispers of starlight weave the most beautiful dreams for you. In the boundless embrace of the universe, Sleep peacefully. Good night, dear interstellar traveler. May you find the most serene rest under the watchful stars.